Okay. Hi, everybody. This is the pre-lab talk for the Anacids lab experiment. Going into a little more detail about titrations, building on what we learned last week, and doing technically something called a back titration. So this, instead of a chelation titration like we did last week, this is an acid-base titration, where the two things you're looking at, one is an acid, one is a base, and you're trying to determine the concentration of one of those. It doesn't always have to be a specific one. For example, you're not always finding the concentration of an acid. Sometimes it's either depending on how your experiment is set up. Again, it's still a titration, so it relies on both the acid and the base being fully consumed at the end so that you can do your stoichiometric calculations to get the concentrations. Because acids and bases react to neutralize each other, it is called a neutralization reaction. And again, like every other titration, the whole point is to find the concentration of one of them, whichever is your unknown. So in an acid-base titration, like every other titration, one of them is your analyte. It is the unknown concentration. Again, does not have to specifically be the acid or the base, but it will be one of them. The titrant is what you know information about, meaning you know the volume, you know the concentration. It's what's in your burette. So analyte, unknown in your Erlenmeyer flask, titrant, known in your burette. And you react them together through a titration process to find the concentration of whichever one is your unknown, the analyte, in your Erlenmeyer flask. Again, reaching the endpoint is dependent on how you've got it set up. You can either use a chemical indicator to do a colorimetric titration, which is what we use to get that color change, or specifically because you're doing acid-base titrations, you can use a pH meter. The Gen Chem 2 labs usually go through this, and Gen Chem 2 lecture covers a whole lot about this. So it's a little bit more complicated and outside of what we want to deal with for this lab. So we're going to use colors. Again, the analyte, you don't know its concentration in the Erlenmeyer flask, in your titration flask. The titrant has known concentration in your burette. The chemical indicator is added to your analyte, is added to your Erlenmeyer flask to monitor the endpoint through a color change. Like last week, we had a color change that was the chemicals itself. This week, we need to add an indicator. We will specifically be using this first one, phenolphthalein. Pain in the butt to say, harder to spell. Another one that we could use is called bromothymol blue. Phenolphthalein goes clear to pink. Bromothymol blue usually turns between yellow and blue. And the choice of indicator really depends on what pH you want your endpoint to be near, or where you expect it to be near. Different indicators will change colors at different pH ranges. So again, same titration setup. You have your Erlenmeyer flask with your analyte and your indicator sitting below your burette that holds your titrant. You still have your clamp stand and your clamp, maybe a funnel, all of that same stuff. You'll start out, especially for phenolphthalein for this experiment, everything will be clear. As you add your titrant, you'll start to see pink coloring appear. But as you swirl the flask, it'll go back clear. And you'll get to a point where a single drop of titrant out of your burette will turn the entire thing pink. Just like last week, a single drop turned it from that really deep red to kind of the yellow-orange color we wanted. Same thing will happen this week, but it should be even more pronounced. It will go from clear to pink. Again, same glassware as the titration. Erlenmeyer flask holds the specific volume of your analyte. The burette holds the known concentration and volume of your titrant. This used to be the first and only experiment where we covered titrations, which is why you see a addition. And when you guys see what the experiment entails and the calculations, hopefully you'll see why we added a titration experiment before this, because it was a lot for brand new. So all of the concentrations are determined the same way we did last week. You'll do stoichiometric conversions or dimensional analysis, whatever you want to call it. It's all the same thing to find that concentration. You know the volume and molarity of your titrant, so you can find the moles of titrant. Because you know the reaction, you can go from moles of titrant to moles of analyte using their coefficients. And then you can go from moles of analyte using the volume of analyte to find the concentration of your analyte. So for example, similar to the calculations we did last week, if you're using a 1-to-1 mole ratio, for example, reacting HBr and NaOH, you have this chemical equation. If you know the volume of NaOH that you add and the molarity, in this case 0.01580 molar NaOH, you do all the dimensional analysis, you use your 1-to-1 conversion because there are no numbers written in front of HBr and NaOH. It is assumed to be a 1. And then you know in this case, you know the molarity of HBr, so you can figure out how much HBr you'll need to add. So what this would look like in the real world is if you know the volume and concentration of NaOH, how much HBr do you need to add to it? And it comes out as 37.26 milliliters. What you can also do is find the concentration. If you knew the volume of your HBr, but not the concentration, you could do something very similar and get the moles divided by the liters to find the concentration of HBr. If it's a 2-to-1 or a 1-to-2 mole ratio, it's the exact same steps. The only thing that changes is when you're looking at the molar ratios, there's now a 2 in front of the HBr, so we need to put a 2 mole of HBr. And for barium hydroxide, it still has no coefficient, so we assume it's a 1. And everything else works out exactly the same. It's all the same steps. In this case, we used the same numbers to get something very similar. But everything else, all the steps, the procedure is done exactly the same. So what we want to do this time is figure out the moles of base in an antacid tablet. So what we're going to have to do is crush up an antacid tablet, and we need to add, the antacid tablet is going to have base in it. That's the way they work. Antacids neutralize some acid to get rid of heartburn and gastrointestinal distress by using a base. So what we need to do is add a ton of acid to our antacid. Make sure we consume all of the base in that antacid, then do a back titration to figure out how much acid was left over. And so again, we've got some steps here. I'll go through some of the more specific steps in just a minute. But we're going to measure out a certain volume and a known concentration of HCl. So we know the moles of HCl in our Erlenmeyer flask. And this experiment is set up so that this is a ton of moles compared to the number of moles in your antacid tablet. When we add the antacid tablet to it, the base in the antacid will react with the hydrochloric acid to neutralize some of it. But there's no way for us to know directly how many moles of HCl it neutralized. We just know some. So that's why this circle is a little bit paler. We know that some of this blue has gone away, but not how much. Then what we're going to do is add our titrant, add NaOH to it, just like a normal titration, until we've filled and neutralized all of these moles of HCl. So just like a normal titration calculation, we can use the volume and molarity of NaOH to figure out the moles of NaOH, to figure out how many moles of HCl were neutralized, which tells us how many moles of HCl were left over. So if we know the moles of HCl we started with and the moles of HCl left over, the difference in those moles is the moles of HCl that the antacid neutralized. So this is why it's called a back titration, is if you think about it this way, we have some base, we add a ton of acid to it, and we go way past the endpoint, so we're way in the acid range. This is no longer neutralized. Then we're going to go back to our endpoint by adding more base, this NaOH, until we reach our endpoint. So we're overshooting our endpoint to then go back to our endpoint so we can do all of the calculations necessary. So again, this used to be the one and only titration experiment. These are much more complicated. So build from what you learned last week, do those titration calculations, and then you just have to add on the little component of how much HCl did you start with, how much did you find in your titration. The difference is how much your antacid got rid of. So again, I kind of have a sort of short key for how to do all of these calculations. Again, I will be going through a separate calculations video where I write out all of the math and show you step by step how to do all of these calculations. There is one important thing to know though. Most antacids, if you Google it, they work through neutralization, but they also work through a buffer system. And without getting too much into what a buffer system is, buffers resist changes in pH. So if we want the HCl and the NaOH to react together for our titration, we need to make sure there is no buffer in our system. Most of the time, the buffer that's created is a carbonate, bicarbonate, carbon dioxide buffer system. Let's see, do I have? I'll put it here. So you end up with some carbonic acid. And where all of this comes from is the antacid tablet. A lot of antacid tablets use some kind of carbonate active ingredient, which forms this buffer system. If you ever look at Alka-Seltzer tablets, when they fizz, that's them releasing various bicarbonates that get turned into CO2, carbon dioxide, that then bubble out. So what we have to do for our system is to make sure there's no buffer in it. We have to boil all of that CO2 out of our system. And I believe one of the post-lab questions asks about this buffer system and asks you to look into it. And there's something called Le Chatelier's principle that you'll need to look into. But basically, if we add one of these carbonate, bicarbonate, carbonic acids to our system, we get this reaction where all of these get made. It just kind of reacts with water and creates all of these options. If an acid or base comes in, it ends up reacting with one of these carbonate systems instead of the acid or base you want it to. And that's why it resists changes in pH. So we need to get rid of this whole system before we add our HCl. I'm sorry, before we add our NaOH in our titration. Because if we don't, we'll add NaOH and it'll react with these carbonates, and we'll have to add more and more and more until we get rid of all the carbonates. Then we can react with the HCl. So instead, we can boil all of this out and get all of those bubbles out of our system, and then we don't have the buffer to deal with, and all of our calculations will be accurate. The carbonate buffer system is actually also important in the human body. That's what your blood and a lot of systems in your body use to help buffer and resist changes in pH. So again, look into that some if you want some little context for why this matters. But I'll go through this in the experiment video, but I have to boil out all of these samples to get rid of this buffer system. Otherwise, I'll end up adding way more NaOH than I need, and all of the calculations will be off. So that's mentioned over here. We need to make sure we boil it. You definitely have to add phenolphthalein to the flask. That's something that a lot of students miss. They'll do this titration and everything will stay clear forever, and they have no clue what's going on. They'll say, hey, Greg, I don't know what's going on. I'll walk over, add a single drop of phenolphthalein, they'll turn bright, bright pink. So then you have to redo that one. So make sure the indicator's in there, make sure you boil it, and you'll see me go through all of this as I do the experiment. So that's the pre-lab talk. And make sure you guys watch the experiment video to see how all of this works out. And if you need any help with the calculations, there will be a calculations video and you can reach out to me. So thanks.